Now that we've introduced enthalpy, I'd like to talk about how to manipulate enthalpy and how to determine what it is without having to do a calorimetry experiment. So for this, we're going to talk about Hess's law. Hess's law states that the change in enthalpy for a stepwise process is the sum of the enthalpy changes of each of the steps. So if I can take a chemical reaction and break it up into two smaller chemical reactions, two stepwise ones that would sum together to equal my overall reaction, then I can take the sum of the enthalpies of those two to find the enthalpy of the reaction I'm interested in. So if I take my overall reaction that A plus 2B becomes 2D, I could break this up if I know that A plus 2B becomes C and that C becomes 2D. If I take the sum of these two reactions to take everything on the right side and left side and add them together, I would have A plus 2B plus C becomes C plus 2D. And I can essentially cancel out those C's on both sides, kind of like our net ionic equations, since it's the same on each side of my arrow. And so if I can take these two equations and make them sum the one I'm interested in, I can take the sum of the two equations enthalpies and get the enthalpy for the reaction I'm interested in. And so when we do this, we apply a few rules that help us manipulate the enthalpies of reaction that we either have already calculated, or a number of them are so common that they're actually published in like the CRC handbook. And so we can actually look up that information. And so we'll go through these kind of three rules. First, when a reaction is multiplied by a factor, like 2, and so all of the coefficients are multiplied by 2, then we also multiply the enthalpy of the reaction by that number as well. If a reaction is reversed, which means I make my products my reactants, then what I'm going to do is change the sign of enthalpy. And if a reaction can be expressed as a series of steps, then that overall reaction becomes the sum of the enthalpy for those steps. Let's look at an example. I think that helps this clarify this quite a bit. First, so you can come back and reference this later, here is a list of steps to take to solve these Hess's law enthalpy reaction problems. And so this is something you can come back to later when you're working on practice problems as kind of a step-by-step method of what I'm about to do. And, and in general, it's advice like choose the most complex compound in the equation for a one-step path, then choose an equation for the multi-step path that contains that same compound. Write down the equation so the compound's on the right side of the equation compared to what you're interested in, and then manipulate the enthalpy to match any manipulations you did to that equation. So if you had to flip it, you multiply it by -1. And you do that for all the different compounds. And sometimes you might have to multiply all the coefficients by a single number, and then you do that for the enthalpy too. If you flip it, you multiply the enthalpy by -1. And you manipulate all of the chemical reactions until when you add them up, things cancel out until you have the reaction you're interested in as the sum. And then you take the sum of the enthalpies and how they've been manipulated to get the enthalpy for the reaction. So here's an example of hydrogen peroxide disproportionating into water in half of an oxygen. And so the information that's given here are two chemical reactions that we have that we can look up the values for in a table, right? And so we can pull this information out of the scientific literature. And so looking at this, I can see that my 1/2 oxygen, I can find right here in my reaction, my first one. And this reaction has an enthalpy of -286. So this oxygen is on the product side of the reaction in both of these equations, so I don't need to flip my new reaction here. And it has the same coefficient, so I don't need to multiply it by anything either. Now, next, let's look at the hydrogen peroxide right here. I found that in my second equation. It's not anywhere in the first, but it is in the second. But this is on the wrong side. It's a product and not a reactant. So I really need to flip this around. So I need to switch my products and reactants. And so when I do that, I essentially multiply everything by -1. And so that -1 is going to apply to the enthalpy, and it's going to apply to the equation. And the effect of on the equation is that it reverses it. The products become the reactants. So now what I'm going to do is add these up. My hydrogen peroxide now is on my reactant side. My hydrogen and oxygen are on my product side. And then for my other one, we didn't actually manipulate it at all. So I still have my half of an oxygen in my water right here, and then hydrogen and oxygen. Now that I have everything written out in one equation, taking the sum of these two, I'm going to cancel out anything that's the same on either side. So I can cancel out these one hydrogen on each side and one oxygen on each side. And that's all I can cancel. So then I rewrite this simplified, and I have something that looks exactly like the reaction I'm interested in. So that means I can calculate the enthalpy of reaction from the enthalpies of the reaction of the two stepwise reactions. So I didn't manipulate this 286 kilojoules. So that negative 286 kilojoules comes here. My negative 88 kilojoules was multiplied by -1, so that becomes a positive 88 kilojoules. I add these together, and I get a value that is negative 98 kilojoules. And that represents the enthalpy of the reaction for the disproportionation of hydrogen peroxide into water and half a molecule of oxygen.